Hey everybody, this is Jake with Jake's Math Lessons TV. Got another problem for you here today. I'm going to be touching again on some related rates problems. Like I said in the last video, next few are probably going to be related rates problems. So today I got another sphere problem for you. This time we're going to be dealing with the surface area rather than the volume. Before I get started though, I do also want to point out I do have a page on my site where I go through this problem, all written step by step. Lots of, maybe slightly different explanation on that page. So I'll throw a link down in the description, and I definitely would recommend that you check that out. Maybe follow along as you watch the video. Might make things make a little bit more sense for you. But anyway, we'll go ahead and jump into this problem. So we're going to, we have this problem here. If a snowball melts so that its surface area decreases at a rate of 1 centimeter squared per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. So just like I've done with all my related rates problems on my site and on my YouTube channel here, we're going to follow the same four-step process. So generally when we're solving a related rates problem, we're going to go through these same 4 steps, and so it's a good thing to take with you and apply to pretty much any problem. So the first of those 4 steps is to draw a sketch. So the first thing we want to do is just kind of take the words in the problem basically and turn that into a picture so that we can visualize what's going on, which will help us come up with our equation later. So we know we have a snowball, which we'll assume it's a perfect sphere. Obviously that's going to be kind of the general shape it's in, but we'll just assume it's a nice perfect sphere. And we know that it's melting so that its surface area is decreasing at a rate of 1 square centimeter per minute. It's not really a good way to represent surface area here, but I'll just kind of draw a down arrow because it's decreasing, and it's decreasing at a rate of 1. Alright. And then we need to find the rate at which the diameter is decreasing when the diameter is 10 centimeters. So at this one moment that we care about, we know that the diameter is 10. So the diameter of a sphere is just going to be the distance from one edge to the exact opposite edge through the center of the sphere. And then also, just to kind of make a note here, it does say find the rate at which the diameter decreases. So we're looking for the rate of change of the diameter. So I'll just write over here dd dt, which just represents the rate of change of the diameter, and obviously we don't know that. That's what we're looking for. So just to kind of make a note so that we can kind of keep that in mind. So here's what we got. We have a sphere decreasing, slowly shrinking as it melts, and we're concerned with the one instant when the diameter is 10 centimeters. So then once we've got our sketch down, the next step that we're going to want to do with any related rates problem is to come up with our equation. So this equation is going to be, what we're going to eventually take the derivative of, but for now we just need to come up with an equation relating quantities rather than rates of change. So our equation shouldn't have any rate of change in it. It should just be like a volume, a diameter, a radius, some sort of distance measurement, some sort of physical measurement. So that's where your drawing kind of comes in handy. We know we have a sphere here. Clearly we have some information about the surface area. So we know that, our equation can use any sort of dimensions of the sphere, like radius or diameter. And then surface area is obviously something we know about, but we'll get into that in just a second. first thing I like to start with when you're coming up with your equation is to think about what are we looking for? What is the question telling us to find? Because this is going to dictate what variable we absolutely need to include in our equation. Because obviously if it's not included, we're not going to be able to get to what we're looking for. So it tells us to find the rate at which the diameter is changing. Rate at which it decreases, which essentially just means the rate of change of the diameter. So we know that we're looking, like I just said kind of a second ago, we're looking for the rate of change of the diameter, right? So as I just said, we don't want rates of change in our equation, so we should not include dt in our equation. But what we want to think about is once we take the derivative of our equation, what should be in there so that we end up with a dt once the derivative has been taken? Well, dt basically just means the derivative with respect to time of the diameter, right? So this d here would be the diameter. So if we know that we need the derivative of the diameter to be in the equation after we take the derivative, that means we must need to put the diameter in the equation before we take the derivative. So this step here just kind of tells us we want to make sure that our equation has diameter somewhere in there. So once we know what we're looking for and how to get to that and what needs to be there as a result of that, the next thing I like to think about is what information do we actually know something about? Clearly we've been given some actual quantity for the rate of change of the surface area, right? It says the surface area is decreasing at this rate. So we know the rate of change of the surface area. So we'll say that surface area is represented by S. So the rate of change of the surface area with respect to time, we know about that, right? We know it's 1 square centimeter per minute. And it also says at this one instant we care about, we're looking at when the diameter is 10 centimeters. So we also know that the diameter is 10 centimeters. So this is really all we know. We know we're dealing with a sphere. We know some information about its surface area, or I guess its rate of change, the surface area's rate of change. We know some information about the diameter. So what that tells us is, obviously we knew from the last slide we need to put diameter in our equation. We need a d in there. This pretty much just kind of reassures that we actually know something about the diameter, so we're not going to cause any problems, I guess, by putting the diameter in there. But really we needed it anyway, so this is helpful. The other thing is the rate of change of the surface area. So all that really tells us is basically that it's okay if we put just the surface area into our equation, because if we're putting surface area, once we take the derivative of our equation, we're going to end up with ds dt. So putting surface area in our equation is something that we can deal with because we know some information about its derivative. Okay, so at this point, really all we've figured out is we need to put d in our equation, and we can put s in our equation, or surface area. So now when we kind of put that all together, really what you want to think about is the geometric shape you're dealing with, which in our case is a sphere. What equation exists that relates the surface area of the sphere with the diameter? Well, you probably have seen the equation for the surface area of a sphere in regards to the radius, and that equation is the surface area, I'll just call it S, equals for squared. So 4 pi is just a constant. Obviously that won't really matter what variables we're using. We also, like I said in the last slide, or the last kind of section, we know that we can put an s in our equation, so this is okay. However, we don't know anything about r, and we don't know anything about the rate of change of r, or the radius, and we aren't necessarily looking for the rate of change of the radius. Of course, the radius is closely related to diameter, so we can deal with this by acknowledging the fact that the diameter of a sphere or a circle is always just going to be twice as much as the radius, right? So d is always going to be 2r. If we rearrange this equation a bit, right, divide both sides by 2, we'll see that r is 1/2 of the diameter. So if we take this for r, we know that r equals 1/2 d. D is something that needs to be in our equation. So actually we can just take this and replace our r with the d, with this 1/2 d, and what that'll give us is an equation that has everything that we want it to have, basically. So let's go ahead and do that. So we'll just replace the r with 1/2 d. And remember, it was squared. So now this is an equation which has the d that we need. It has the s that we know how to deal with, and that's the only variables. Other than that, it's just constants. So this is a good equation that we can go ahead and use now. So what I will do is just kind of grab this, and we'll take this equation and go on to our next step here. So now once we have created our equation, which we just did, we can do the implicit differentiation step, which essentially just means take the derivative of both sides of the equation with respect to time. However, before I do that, I would like to, oh yikes. Before I do that, I would like to simplify this equation. Because it's going to make things a lot easier for us. So let's just shrink this down a bit. So I'll go ahead and deal with this squared piece. 1/2 d squared, all we really need to 1/2 d squared. All we really need to do is basically square each of these pieces. So the 1/2 piece squared would be 1/4. And then the d piece squared will be d squared. And then we keep our 4 pi here. And then to simplify this, we have 4 times 1/4, so those will actually cancel. And all we're going to have then is pi d squared equals our surface area. Okay, so that's going to be our equation that we want to take the derivative of. So now all we need to do is just take the derivative of both sides of this equation. So basically all that means is we're going to take the derivative of this whole thing with respect to time. So to do that, we're going to need to realize that we're treating our variable s and d as if they are functions of time. So we don't know what they are. We don't have an explicit function for s or for d, but we know they're functions of time. So when we're taking the derivative of s, for example, our left side, with respect to time, since we don't have an explicit formula for s, we aren't going to be able to have an explicit formula for the derivative of s. So really the best we can do there is just to say that the derivative of s is just ds dt. And then over on our left side, over on our right side, we're taking the derivative of pi d squared. So when you're taking the derivative of a constant times something else, the constant will basically just carry through. So we're just going to get our pi to carry through. And then the d squared is going to require the chain rule, right? Because, like I said, d is a function of time, which we don't know, but it is a function. So when we have d squared, that's basically some function squared, which is basically some function plugged into another function, which is the squaring piece. So to do the chain rule, we'll need to do the derivative of the outside, leave the inside alone. So here our outside is the squared piece, and our inside is the d. So to take the derivative of the outside, we would essentially just, the derivative of the squared piece, use the power rule. So bring the 2 down in front and lower the power by 1. So leave our inside alone. And lower the power by 1 would just make it a 1, basically, which anything to the first power is just itself, so that doesn't really do anything. And then, based on the chain rule, now we need to multiply this by the derivative of the inside. So our inside is d. To find the derivative of d, it's going to be just like s. We don't really know what d is. Therefore, we can't know its derivative. So the best we can do is just to say dd dt. Okay, so here's our derivative. That's really all it takes to find the derivative there. So now there's not really a whole lot of simplifying we could do here. I mean, we could rearrange things a bit, but it's not really going to make things any simpler. So we'll just grab this and take it along to our next step. So finally, what we need to do is solve for the rate of change that the question is asking us. Right, so this question is asking us to find the rate of change of the diameter. Right, the rate at which the diameter decreases. So the rate of change of the diameter is exactly what is represented by dd dt, right? That's just the rate of change of the diameter. So now all we really need to do is just solve for dd dt. So to do that, we first of all need to isolate it, right? So we want to get that piece of the equation all by itself on one side of the equation. Since we just have dd dt multiplied by all this other stuff, the pi times 2d, we can basically just divide both sides or multiply both sides by 1 over all of that in order to move it over. So basically we're just going to do just that. So our ds dt will still be here. And then we're going to multiply it by 1 over pi times 2d. And that will leave us with the dd dt all by itself on the other side of the equation. Right, so we've solved for our dd dt. Now all we need to do is plug in the values that we have for for ds dt and for d, right? Because those are, obviously not numbers. We need to plug something in for those so that we can figure out the actual value of dd dt. So to do that, we know that the surface area is decreasing at a rate of 1 squared centimeter per minute. So basically what that tells us is, since it's decreasing, ds dt is going to be a negative number, and we know that it's decreasing at a rate of 1 squared centimeter per minute. So ds dt is going to be -1. And then d is pretty simple. It tells us the diameter is 10 centimeters. So d is going to be 10. Right? So if we take these two values here for ds dt and for d, plug those into our equation over here, that'll tell us that dd dt equals -1 times one over 2 pi times d, which is 10. Right, so our rate of change of our diameter is just -1 times 1 over 2 pi times 10, which we can simplify a bit. Before I do that, let's just clear some of this stuff out here. So that tells us that dd dt is -1 over 20 pi. So that's it. We know that the diameter is decreasing at a rate, well, it is changing at a rate of -1 over 20 pi, which the negative is essentially the same as saying decreasing. So the diameter is decreasing at a rate of 1 over 20 pi centimeters per minute. So really, since it's asking us to find the rate at which the diameter is decreasing, our answer is actually going to be positive, because the negative is the same as saying that it's decreasing. So we know that our diameter is decreasing at a rate of 1 over 20 pi centimeters per minute. And that's it. That's all it takes. So like I said before, the same 4-step process can be applied to basically any related rates problem. They're all going to be, the same 4 steps. Like I said, go check out the page in the description. I'll post a link. Page where I go through all this step by step. It'll be maybe a good reference for you to go back and look at that. Maybe follow along, while I'm working on it. So go check that out, and I'll be posting plenty of more videos here of different problems. Like I said before, most of the next few are going to be related rates problems. So if you want some more practice on related rates problems, come back. I'll be having plenty more coming soon. Hope you enjoyed, and hopefully this was helpful for you. If you have any questions, definitely post questions in the comment section. Email me questions. You can go to my site, and there's contact info on there that you can email me any questions you have. I'd love to hear from you, so hope to hear from you soon. Thanks for watching.